Ever wondered how AI can answer super specific questions accurately, even about things it wasn't trained on? That's where Retrieval-Augmented Generation, or RAG, comes in.
RAG is a game changer for making AI more reliable and useful, especially when dealing with factual, up-to-date, or proprietary information.
Today, we're going on a journey to demystify RAG. We'll cover why we need it, how it works, its components, and real-world applications.
Large language models are amazing, but sometimes they confidently make up information, a problem we call hallucinations. They just invent facts.
Most LLMs have a knowledge cutoff date. This means they can't tell you about recent events or information that emerged after their training.
Without specific context, LLMs often give very general answers. They struggle with niche questions about your personal data or company documents.
When an LLM gives an answer, it doesn't usually tell you where it got that information. This makes it hard to verify or trust the output.
Constantly retraining an LLM to update its knowledge or add new information is incredibly expensive and time-consuming. It's simply not practical for dynamic data.
Imagine an LLM taking an open book exam. Instead of relying only on what it memorized, it can look up information from a provided textbook to answer questions.
RAG combines two powerful ideas: retrieval, finding relevant information, and generation, using an LLM to formulate an answer based on that information.
The goal of RAG is to provide answers that are factual, current, specific to your data, and crucially include sources so you can verify them.
At a high level, RAG involves two main phases. First, preparing your knowledge base and then using it to answer user queries.
The first phase is called indexing. This happens offline where we process all your documents and prepare them for fast retrieval later.
When a user asks a question, RAG first retrieves relevant pieces of information from your prepared knowledge base.
Finally, the retrieved information is given to an LLM, which then generates a coherent and accurate answer citing its sources.
Let's break down the full cycle, from your raw data through indexing to answering a user's question. It's a precise pipeline.
Chunking is the process of breaking down large documents into smaller, more digestible pieces or chunks. Think of it like chapters in a book.
Why do this? LLMs have a limited context window. They can only process so much text at once. Chunks fit within this window, making retrieval efficient.
The simplest method is fixed-size chunking. We just cut documents into pieces of a specific length, often with some overlap to maintain context.
More advanced strategies try to chunk semantically, keeping related ideas together. This might involve splitting by paragraphs, sections, or even using AI to find natural breaks.
Once we have our chunks, we convert them into embeddings. These are numerical representations like coordinates in a vast conceptual space.
Embeddings are powerful because they capture the meaning of the text. Chunks with similar meanings will have embeddings that are numerically close to each other.
Think of it as a multidimensional space. Every word, sentence, or chunk is a vector in this space. The direction and distance of these vectors encode their semantic relationships.
These numerical representations are created by embedding models, which are specialized neural networks trained to understand and map text into these vector spaces.
Once we have all our chunks converted into embeddings, we store them in a vector database. This specialized database is designed for efficiently storing and searching these high-dimensional vectors.
Traditional databases struggle with vector similarity search. Vector databases use clever indexing techniques to quickly find the most similar vectors to your query, even among millions.
They often employ algorithms like approximate nearest neighbor (ANN) search. When you provide a query embedding, it rapidly finds the most similar document chunks.
Popular vector databases include Pinecone, Weaviate, Milvus, and ChromaDB. Many traditional databases are also adding vector capabilities.
Now for the retrieval phase. When a user asks a question, we convert their query into an embedding, just like our document chunks.
This query embedding is then used to search the vector database. We look for document chunks whose embeddings are most similar or closest to the query's embedding.
Often, RAG systems use hybrid search, combining vector similarity with traditional keyword search. This helps catch both semantic matches and exact keyword hits.
The initial retrieved chunks might not all be equally relevant. Reranking uses a smaller, more powerful model to sort the retrieved chunks, placing the most pertinent ones at the top.
Sometimes, the original user query isn't ideal for retrieval. Techniques like query transformation can rewrite or expand the query to improve search results.
The most relevant chunks are then injected into the LLM's prompt as context. This is like giving the LLM an instruction manual before it answers.
With this context, the LLM no longer has to guess or hallucinate. It synthesizes the information from the provided chunks to formulate a coherent, accurate answer.
The final output is the generated answer, often accompanied by direct links or references to the original document chunks. This builds trust and allows verification.
The simplest form, naive RAG, involves basic chunking, standard embeddings, and direct retrieval. It's a great starting point but has limitations.
Advanced RAG incorporates techniques like query transformation, re-ranking, and context-aware chunking to significantly improve retrieval quality.
Modular RAG emphasizes a flexible architecture where different components, chunkers, embedders, retrievers, can be swapped out and optimized independently.
Self-RAG is an exciting new approach where the LLM itself generates and evaluates intermediate retrieval steps, reflecting on its own process to improve accuracy.
RAG is perfect for building customer support chatbots that can answer specific questions about your products or services using your internal documentation.
For large organizations, RAG can transform how employees find information, providing instant, accurate answers from mountains of internal data.
Researchers can use RAG to quickly synthesize information from vast academic papers, scientific journals, or legal documents, saving countless hours.
In education, RAG can power personalized learning tools that adapt to individual student questions and provide tailored explanations from course materials.
One of the biggest challenges is poor retrieval. If the system retrieves irrelevant or insufficient chunks, the LLM can't generate a good answer.
Even with chunking, the LLM's context window can still be a bottleneck. Too many chunks, or very long ones, might exceed its capacity.
Retrieving chunks and then generating an answer takes time. For real-time applications, this latency can be a problem, leading to slow responses.
Running embedding models, vector databases, and powerful LLMs for every query can incur significant computational costs, especially at scale.
To improve RAG, start with better chunking. Experiment with different chunk sizes, overlaps, and semantic splitting to ensure context is preserved.
The choice of embedding model matters. Use a model that's well suited for your domain and data type to create more accurate and meaningful representations.
Implement advanced retrieval techniques like query transformation, re-ranking, and multi-stage retrieval to find the absolute best chunks for the LLM.
While RAG avoids full retraining, you can fine-tune the LLM on a small dataset of question-answer pairs to improve its ability to synthesize and format answers from retrieved context.
Crucially, measure your RAG system's performance using metrics like context relevance, faithfulness, and answer quality. Iterate and improve based on these.
RAG is about providing external asterisk knowledge at query time. It's like giving the LLM a fresh textbook for every question.
Fine-tuning, on the other hand, bakes internal asterisk knowledge directly into the LLM's weights. It's like teaching the LLM new facts it then remembers.
RAG excels with dynamic, frequently updated data. You simply update your vector database, and the LLM instantly has access to the latest information.
Fine-tuning is better for static, unchanging knowledge or for adapting the LLM's style, tone, or specific output format.
The best approach often combines both. Fine-tune an LLM for your specific domain style, then use RAG to provide it with up-to-date external facts.
A real RAG architecture involves several key components working together: data sources, indexing pipeline, retrieval system, and the LLM orchestrator.
Your data can come from anywhere: PDFs, websites, databases, internal wikis, or even live APIs. The more diverse, the better.
This pipeline takes raw data, chunks it, embeds it, and loads it into the vector database. It often involves data cleaning and preprocessing.
This is where the magic happens. It receives the user query, converts it to an embedding, searches the vector DB, and potentially re-ranks the results.
This component takes the user query and the retrieved context, constructs the final prompt for the LLM, and then processes the LLM's generated response.
Finally, the user interface. This could be a chatbot, a search bar, or any application where the user interacts with the RAG system.
Building RAG systems is made easier with frameworks like LangChain and LlamaIndex. They provide pre-built modules for chunking, embedding, retrieval, and LLM integration.
Deploying a RAG system involves hosting the vector database, embedding models, and the LLM. Cloud platforms offer scalable solutions for each component.
Continuous monitoring of retrieval quality, LLM responses, and system latency is vital for maintaining performance and identifying areas for improvement.
RAG is an iterative process. You'll constantly refine your chunking, experiment with embedding models, and fine-tune retrieval strategies based on feedback.
So what are the key takeaways? RAG solves LLM limitations by giving them an open book of external, up-to-date knowledge.
It involves an indexing phase to prepare your data and a retrieval generation phase to answer queries with context.
Components like chunking, embeddings, and vector databases are crucial for efficient and accurate information retrieval.
RAG is highly adaptable and can be combined with fine-tuning for even more powerful and tailored AI applications.
The future of RAG is bright. Expect even smarter retrieval, more sophisticated generation, and seamless integration into everyday AI tools.
We'll see RAG extend beyond text to multimodal data, allowing AI to retrieve and generate answers from images, audio, and video.
RAG will be a core component of AI agents that can perform complex tasks by planning, retrieving tools, and executing steps autonomously.
RAG empowers LLMs to be truthful, current, and incredibly useful. It's a foundational technique for building the next generation of AI applications.
Thank you for joining this deep dive into RAG. Explore the resources in the description to start your own RAG journey. Don't forget to like and subscribe.